Today we're going to be doing the molecular orbital diagram theory for N2 plus. My name's Christina Shryock. So we're going to get started. So 1s, we know that that's filled on both sides. This is going to be the atomic orbital, and this one also, and this is going to be the molecular orbital. So we know that those two are filled for sure. So this is going to be sigma 1s, and this is going to be sigma star 1s. The star represents anti-bonding, and the one with no star represents bonding. We're always going to start with the bonding orbital in the molecular orbital column. So we're going to start right here. This one gets filled. Then the anti-bonding orbital gets filled. And then same thing here. This is going to be 2s. We know that these are filled based off our periodic table, and they're going to get shared. So this gets filled because there's 4 electrons in each, so it gets all the way filled. We're also going to label the top. So this is going to be N2 plus, N2 plus, and this is going to be N2 because the electron, we're only going to take off the electron from one side. So we know for N2 there's usually 3 electrons, but since there's a plus sign right here, we're only going to give it 2 because 1 electron goes away. So for here, we're going to start with the pi 2 px, pi 2 2py, sigma 2pz, pi star 2py, pi star 2px, sigma star 2pz. We're starting with the pi because we know that for boron, nitrogen, and carbon, there's going to be a larger bond interaction between the 2s to the 2px orbitals. So that's why we start with the 2px on the bottom. So then we're going to go ahead and do the same thing, share the electrons. So we're going to take 1, 2, 3, 4, 5. This is going to be the diagram for N2 plus, and we're going to do the bond order. So we're going to count. Bond order is 1/2 the bonding orbitals minus the anti-bonding orbitals. So for this one, there's going to be 9 bonded minus 5 non-bonded. So this is going to equal 2.5 bonding order. So for our other species, the 1s to the 2s is going to be the same. The only thing that's going to change is for the 2p orbital. So we know like usual that this is going to have 3 for a regular dinitrogen ion. However, on the other side, due to the minus sign, we're going to have an extra electron because we gained 1. So then we're going to start distributing. So this is going to get 1. So there's 2, 3, 4, 5, 6, 7 to distribute. So this is 4, 5, 6, and we're going to get 7 on the top. So from counting our diagram, we see that there's 10 bonded electrons and 5 non-bonded. So this is also going to give us a bonding order of 2.5. And then don't forget that this is going to be your atomic orbital, your molecular orbital, and then another atomic orbital. So we do know that this species does exist in a very unstable state. So these two species are going to have the same bond length. They're also going to have the same bond strength. However, looking more deep into the bond strength, we're going to come to find out that N2 minus is going to be slightly stronger due to the fact that it has less electrons in the anti-bonding orbital, making it more stable, still unstable, but making it more stable than N2 minus. And both of these species are going to be paramagnetic due to the fact that both of them have lone pairs in either their anti-bonding orbital or the bonding orbital. And lastly, the purpose of the molecular orbital theory diagram is going to be that it allows us to predict the distribution of electrons within a molecule. Thank you.